So let's start by working out the empirical formulae for some examples. Remember that when a chemist actually measures things in the laboratory, they cannot directly measure what the formula of the substance will be. They can measure the mass ratio of the different elements in a substance. And then we can convert that mass ratio into a particle ratio by using molar mass from the periodic table. And the particle ratio gives us the formula. When in the simplest form, that's an empirical formula. So a chemist measures that a certain compound is composed of so many grams of sodium, so many grams of sulfur, and so many grams of oxygen. We have to find the empirical formula of the compound. So the elements inside this compound are sodium, sulfur, and oxygen. And the mass ratio that the chemist has measured is 6,027 grams of sodium for every 8,474 grams of sulfur and 6,336 grams of oxygen. So this is a mass ratio, but the formula contains a mole ratio, a particle ratio. So let's convert this mass ratio into a particle ratio. So that's been done for us already for sodium, 0,26 moles of sodium. Let's do it for sulfur. How many moles of sulfur is 8,474 grams of sulfur? We multiply that by a conversion factor, which has grams of sulfur at the bottom, mole of sulfur at the top. In other words, we use the molar mass of sulfur. 32 grams is the mass of 1 mole of sulfur. 8,474 divided by 32, 0,26 mole of sulfur. How many moles of oxygen have a mass of 6,336 grams? Multiplied by a conversion factor, grams at the bottom, mole of O at the top. Notice it's mole of O, not mole of O2, because here we're not speaking about oxygen gas in the atmosphere in the elemental form, but rather oxygen atoms within another compound. We use the periodic table. 1 mole of oxygen atoms has a mass of 16 grams. 6,336 divided by 16 is equal to 0,389, which rounds off to 0,39 moles of oxygen atoms. So here we now do have a mole ratio. So strictly speaking, we could write the formula like this. Na 0,26, S 0,26, O 0,39. But obviously that looks awful, and it suggests that we have partial atoms in a whole molecule, which is stupid. We want whole numbers. We don't want any fractions here. So we need to convert this ratio. Keep the same ratio, but just give it in the format which has only whole numbers within it. So to do that, we need to simplify and possibly multiply. What do I mean? We take the smallest number of all of these, which is 0,26, and we divide each of these numbers by that number. So in this case, it's 0,26 divided by 0,26, which is obviously equal to 1. For now, let's just write equal 1. We'll see later if we need to multiply it by something. Then the same here, 0,26 divided by the smallest number here, which is 0,26, that's equal to 1. And here again, 0,39, again, divided by the smallest number available here, 0,26. And we find that that is equal to 1,5. So now we have a better ratio. Instead of writing this strange formula that I have here, we are keeping the same ratio, just writing it in nicer numbers. Na 1, S1, O 1,5. But it's still not good enough, because that suggests that one Na atom bonds to one S atom and 1.5 O atoms, which doesn't make any sense. So we still don't have it in whole numbers all the way. So we need to multiply everything through by something to clear away the fraction. Obviously, what should we do? Multiply everything by 2. That gives 2 there multiply this one also by 2, gives 2, and multiply this one by 2, and we have 3. And so then we have a ratio 2 is to 2 is to 3, which is the same ratio as 1 is to 1 is to 1,5, and that's the same ratio as 0,26 is to 0,26 is to 0,39. They're all the same ratio. It's just that this last one is the simplest form which has only whole numbers, and that is what we're looking for in the empirical formula of a compound. So that is our formula. Na2S2O3. A chemist measures that a certain compound is 20,19%. Now that percent just means out of 100. So we can take it that the whole mass of the compound is 100 grams. Then each of these percents would just be telling you the mass in grams for a total of 100 grams. So don't be confused by that percent. Remember that percent composition, which is what is being given here, is a mass ratio. And so it's just a different way of writing a mass ratio. And we can take away the percents, replace it with grams to write down our mass ratio. 20,19 grams of magnesium for every 26,64 grams of sulfur and for every 53,16 grams of oxygen. So we've written down our mass ratio. We need a mole ratio. How many moles of magnesium have a mass of 20,19 grams? We multiply by a conversion factor which has grams at the bottom and moles of magnesium at the top. And this conversion factor is the molar mass of magnesium. 24 grams is the mass of 1 mole of magnesium atoms. So if we have 20,19 grams of magnesium atoms, we have 20,19 divided by 24 moles of magnesium atoms, 0,84 moles of magnesium atoms. How many moles of sulfur atoms have a mass of 26,64 grams? Again, we use the molar mass as our conversion factor, making sure that grams are at the bottom to cancel the given unit out, and mole of sulfur atoms at the top. 1 mole of sulfur atoms has a mass of 32 grams. 26.64 divided by 32 is equal to 0,83 mole of sulfur atoms. How many moles of oxygen atoms do we have when we have 53,16 grams of oxygen? That is grams of oxygen atoms, not grams of oxygen molecules. It's not O2. It's O within a compound, so it's not the gas. Again, we use the molar mass as our conversion factor, making sure grams are at the bottom to cancel grams out, and mole at the top. 1 mole of O atoms has a mass of 16 grams. 53.16 divided by 16 is equal to 3,32 moles of O atoms. So here we have a molar ratio, a particle ratio, but we need our particle ratio in the simplest whole number format. How do we get that right? We choose out the smallest number, 0,83, and we divide through everything by that. 0,84 divided by 0,83, 0,83 divided by 0,83, 3,32 divided by 0,83. What do we get? You can see that this is going to basically give 1. If everything was theoretically perfect, we wouldn't have got a difference between the top and the bottom here. But whenever we do things practically, we always get some experimental error, some rounding off error. And that's why you might get situations like this where it might look a little strange because it's not exactly the same number, top and bottom. And for the ratios to be right, it needs to be. But when you round it off, you get a whole number, 1 in this case. Here it's obvious that the answer is 1. 3.32 divided by 0.83 gives us 4. So this is very easy. We don't have to still multiply by something because the first step, just simplifying, has given us whole numbers throughout. So we need not multiply in this particular case. Gives us our empirical formula straight away. Mg1, which we don't write, S1, which we don't write, O4.